welcome everyone. I'm Michael Dukes, not the normal host of the BMP Summit, but I'm filling in because Dr. Sharma is one of our speakers today. And you have joined the 2021, our virtual BMP Summit. Emily has posted the recordings of the previous episodes up on the chat. And after today, by my count, we've got about 3 more weeks, each Tuesday at 1 p.m. So with that, I'll introduce our speakers today. As always, we'll take questions in the chat. You can post them anytime, but we're going to address those after each speaker is finished. So today, I'd like to welcome Dr. Hardev Sandhu, who is an associate professor of agronomy at the Everglades REC in Belgrade. Dr. Sandhu works on sugarcane cultivar development, as well as production of sugarcane. And we're gonna see a picture of that today in his talk on integrated land management and crop rotations. Our second speaker will be Dr. Lakesh Sharma. He's an assistant professor in soil and water science in Gainesville, and he's the statewide best management practice coordinator. And his topic area specialty is soil fertility and sustainable agriculture. So with that, Hardev, the floor is yours.
Thanks, Michael. Good afternoon, everyone. Today I will talk about how we can use the integrated land management practices, and which includes crop rotation to improve our soil health and also crop nutrition. So just a little bit about the background, why we need integrated land management practices. Because of increasing world population, we need more productivity. We are expecting more productivity from our agricultural lands. And that takes us into the intensification of production. That includes more inputs to produce more crop, to improve yields or to get higher yields. We put more inputs, and that can impact our water resources, either through leaching or through runoff. Therefore, the integration of cover crops or rotation crops in our agricultural lands can improve the sustainability of our traditional cropping system. In our today's presentation, I will talk more about integration of bioenergy crops. There are 2 reasons for that. One is I work with bioenergy crops, especially with energy cane. I'm working with energy cane for last 6 years, and we recently got another grant from DOE to keep working on energy cane, and this time it will be used as integrated land management practice in our traditional cropping system. And the other reason is because of the physiological advantage of these perennial bioenergy crops over row crops, such as corn and soybean, and even on sugarcane. For example, energy cane, you can see the pictures over here. This picture is energy cane, which is very high biomass crop and very densely growing species of sugarcane. So the advantages of perennial grasses are their high population, densely growing species with deep rooting system. So the picture on the right side, that shows the rooting system. On the left, it's energy cane roots, and on the right, it's sugarcane roots. So you can see the difference. Although they are from the same genus, they're still, quite different. If you grow energy cane, which is used for cellulosic ethanol production, it's dedicated feedstock for cellulosic ethanol production. So it has very extensive rooting system, and that improves its water and nutrient use efficiency. So these bioenergy crops have very high water and nutrient use efficiency. And they're suitable for addressing water quality problems by minimizing soil erosion. And also they can recover the leached nutrients, which row crops can't. So because of these characteristics, these bioenergy crops are suitable for removing excess nutrients because of deep rooting system. And these nutrients otherwise can leach in the subsurface soil or shallow groundwater system, and they can't be assessed by the shallow rooted um, our annual commodity crops in our traditional cropping system. But there are several challenges of promoting bioenergy crops, and one of them is the competition for land. If we grow more bioenergy crops, we have to acquire more land for food crops because we replace or displace the regular food crops or feed crops and to grow bioenergy crops. So for that, there is a possibility of potential conversion of forests and grasslands to accommodate bioenergy crops, and that can potentially increase greenhouse gas emissions over the long term. However, there is current focus on developing second generation bioenergy crops, for example, grasses and short rotation woody crops, which can improve greenhouse gas emission balance compared to first generation corn ethanol. And that's why I'm going to talk about the integrated land management practices and not just growing the bioenergy crops by displacing or replacing the food or feed crops. So these are some of the perennial grasses which are identified as a suitable bioenergy feedstocks. First is energy cane, which is grown mainly in subtropical and tropical climates. Switchgrass is more suitable for temperate climates. Um, in Midwest, it's more common. Miscanthus is also, it can be grown in both climates depending upon the species. And similarly, the other crops, they're the dedicated feedstocks for cellulosic ethanol production, lignocellulosic ethanol production, and they have the um, benefits of water quality and to improve water quality. So, in the integrated landscape management, we sustainably integrate the crops. For example, these bioenergy crops or cover crops or rotation crops into our traditional cropping system. Um, so that all relies on innovative approaches to land management, which is like more depending on some precision ag technologies. So this integrated approach to food, feed, fiber, and low carbon energy production, it can conserve water quality while maintaining the integrity of other ecosystem services. So here I have three examples, or three major categories of integrated landscape management. One first is double cropping. We can also call it crop rotation, like you rotate with the commodity crops with bioenergy crop. And then it's a mixed cropping and intensified production. So in the figure over here, A is double cropping, where in temperate you can get two crops, in tropics you can get up to three crops. So you are actually rotating the commodity crops with bioenergy crops. In the second figure B, it's mixed cropping. So in this, we don't rotate crops, but we integrate them. I will explain it a little more in the next slide. And then in C, it's the intensified production, which is the combination of both double cropping and mixed cropping. So in double cropping, we take the advantages of temporal availability and suitability of land for growing bioenergy or cover crops. following the harvest of the main crop, which is our commodity crop. So it depends, it's more seasonal. We have to find a crop that can be grown, that can fit in the crop rotation cycle of the commodity crops. So this, if we use this approach, it has advantages. It can provide cover for the bare soil um, if we are not growing anything on that soil during the off season, and then that soil is bare. And if we grow energy cane or bioenergy crop on that um, land during the off season, then it can provide cover and minimize soil erosion. And in addition, it also it can also take advantage of the excess nutrients which we apply to the commodity crop and that stays in the soil, and which can minimize the offsite losses of critical pollutants, particularly nitrate and nitrite. So these are some of the examples which of bioenergy crops that can fit in double cropping system. For example, winter rye, winter triticale, winter camelina, hairy vetch, and turnip rape. These are some of the crops which can fit in in this double cropping systems. And these are the biofuel crops, although not all of them are first generation biofuel crop, but uh, uh, not all of them are a second generation biofuel crop, but first generation. So in one of the studies, at the bottom, there's an example which shows that in one study, they found that if we grow corn only compared to the sole corn cropping system, a corn production doubled. um, in double cropping with winter triticale can reduce up to 34% of nitrogen loss that can be leached into the soil. So the next one is mixed cropping. So in mixed cropping, it's a little bit tricky because it's not simple that we just use that land either for the commodity crop and then rotate it with the other crop. In this one, we take advantage of spatial heterogeneity of the agricultural landscape. That means we have to um, identify the areas which are subfertile or which are, for example, where there is low water table or high water table and the commodity crop can't grow very well and may not yield that good or may not survive. So we identified the areas which are marginal areas within the field, and we can grow bioenergy crops or perennial bioenergy crops in these areas. Similarly, we can also grow these crops at the um, near the water stream or near the water outlet from the field so that they can uptake the excess nutrients from the groundwater before it goes to the stream. So commodity crops can still continue to be grown on most of the field, most of the area in the field, which is fertile and which is good. And bioenergy crop, which they are only for the marginal areas. And there are some of the toolkits which are available to find out where is the marginal zone or marginal areas in your field. So there are few examples where they tried mixed cropping, and by allocating only 10% of the field to prairie strips, this approach reduced 60% of overland flow, 95% of sediment transport, and 90% in phosphorus and total nitrogen losses. So there are studies being conducted already, and which shows that that using these bioenergy crops on in marginal areas can help in in improving the water quality. In intensified production, as I said before, it's combination of both methods. So in this one, we use bioenergy crops on the marginal areas in both crops. I mean, we grow our commodity crop, we rotate it with the bioenergy crop, but in addition to that, we use one perennial grass or perennial bioenergy crop as on the borders or on the marginal areas of that land. So we are combining both mixed cropping and double cropping in this, which is intensified cropping. So um, it takes the advantage of temporal and spatial availability of land because we are combining both methods over here, and it is not supposed to affect the commodity yields, commodity crop yields. In temperate areas, double cropping will likely be dominated by annual crops, which includes winter triticale, winter rye, and winter camelina, as I discussed before. And on the same field, the marginal areas and buffer zones will be grown with perennial grasses. For example, switchgrass or Sugarcane or miscanthus that have that needs low inputs and that can minimize input cost and can recover the excess nutrients from main and double crops. So currently we have a research project that we are going to start in next couple of months, which is mainly um, it's mainly evaluation of energy cane for bioenergy and sustainable agriculture systems. And in this project, we are going to evaluate energy cane for bioenergy production as well as for its ecosystem services that includes its effects on soil and water quality, for example, nitrogen and phosphorus loading, greenhouse gas emissions, and biodiversity in marginal agricultural lands of US Southeast coastal plains. And this is our collaborative project with Argonne National Lab. Now I will switch gears to show you some of the research which we conducted over here in the Everglades agricultural area on muck soil, and um, where we tested the soil properties or we assessed the soil health in different cropping system. For example, sugarcane is a perennial crop. So we plant it one time and we harvest it after 1 year, and then it grows again as a ratoon crop. So it's good for at least 3 to 4 years. And every 3 4 years we take out the last crop and we take out that cane and then cultivate it, and we can either plant sugarcane again in that soil, or we can plant some rotation crop, or we can leave it fallow for 3 to 4 months before we plant next sugarcane crop. So in this case, most of the area in the Everglades agricultural area over here, most of the sugarcane area, they use either rice as a rotation crop or sweet corn as a rotation crop, or they just leave the land fallow for some time and then grow sugarcane again. And then there are two harvesting methods which we assessed. Burnt cane harvest, where they burn the sugarcane or before they harvest, just mainly to get rid of the leafy residue, and so that there's not much trash left on the soil surface after the sugarcane is harvested. In green cane harvest, it's harvested as green so that there's no burning, and then it leaves thick layer of trash of sugarcane trash on the soil surface um, after the cane is harvested, and then that harvest residue or trash is incorporated into the soil. So in this one, our hypothesis was if the fields and the different planting systems would differ in microbial and chemical soil properties. And this work was done by my previous PhD student, and it's published. And I gave the citation over here for more details on this project. So, as I just mentioned, that in the sugarcane planting system, in successive planting, which we also call sugarcane monoculture, we grow sugarcane and then we harvest that after 3-4 years, and we plant sugarcane again immediately after that. Like, just prepare the land and plant sugarcane again. There's no fallow period. On the other hand, in the other planting system, we have a fallow period. So we harvest sugarcane late, and then that is harvested up to April, and then from May to September is fallow period, when we can grow either sweet corn or rice, or we keep it flooded and we keep it fallow, and then we plant it with the sugarcane again in October. So we collected some soil data on soil properties from the fields which had histories of the same kind of cropping system for last 20 years, 15 to 20 years. And we tried to evaluate if there is a difference in the properties. For example, microbial biomass, it's total PLFA biomass, which is phospholipid derived fatty acids, and it indicates the microbial biomass. And in this one, the first one is sugarcane with fallow, and sugarcane with corn, and then sugarcane with rice rotation, and sugarcane with burnt harvest, and sugarcane with green cane harvest. So you can see, if we just go with sugarcane monoculture with burnt cane harvest, where we don't leave any residue on the soil surface and there's no crop rotation, microbial biomass is significantly lower compared to others where we use crop rotation or go with green cane harvest, where we incorporate residue. Similarly, we then divided that into bacterial PLFAs, fungal PLFAs, fungi, bacteria ratios, and then gram positive, gram negative bacteria, saturated, unsaturated ratios. So I will not go into too many details of that, but basically, if you leave the residue or you incorporate the residue in the soil, either through crop rotation or through green cane harvest, that improved the soil properties. The other thing is, if we go with sugarcane monoculture in these soils, we see that there is yield decline compared to crop rotation or fallow system, and that may be linked to the accumulation of harmful fungi, because when we use some fungicide in the soil, it definitely improves yield. So that was another reason that for this study, to find out what's going on in the soil, and if these cropping systems are making any difference in soil microbial properties. So what we found, that with green cane harvest or sweet corn rotation, that showed higher organic matter, total carbon, community metabolic diversity, mycorrhizal fungi abundance, and slow growing bacterial groups. Similarly, the gram negative fungi, gram positive, and other bacterial proteases, these are the ones which explain the highest variation, and that variation between different cropping systems was significant. Explanatory variables were mainly gram negative bacteria and fungi that were the strongest predictors among all the parameters which we assessed in this study. And then we also conducted a smaller study, small plot study, where we used different crop rotations for 2 years to determine its effect on soil properties, and also to see its effect on sugarcane yield, which is planted after these crop rotations. So in this case, because traditionally we only have sweet corn and rice, which is used as a rotation crop. In this one, we compared some leguminous crops, soybean and cowpeas, in the sugarcane monoculture, because sweet corn and sugarcane are from same family, and similarly rice is also from family Poaceae. So there may be some effect of these, if we grow crops from same family again and again, and that may have some negative effect on soil properties. So we incorporated soybean and cowpeas in this planting system, and we evaluate them for biomass production, residue quality, and also to combine their effect with some fungicides, soil fungicides, and see if that also helps in improving sugarcane yields. So these pictures show that bare fallow, where we didn't grow anything during the fallow period. In soybean, was used as crop rotation in the plots where um, we go with the rotation crops, and then the other rotation crops was sweet corn and cowpeas. So what we found that the soil carbon nitrogen ratio, CN ratio, was relatively higher where we incorporated residue from either from sugarcane or from sweet corn, while they were relatively lower where we had cowpea and soybean. Soil microbial communities. So we took samples before we planted sugarcane and at the early growth stage of sugarcane. So after we took out the rotation crops, we planted sugarcane within 2 to 3 weeks. And at pre-plant, we did see some significant differences in the microbial biomass, whereas bare fallow was significantly lower compared to sweet corn, and the others were not significantly different. However, in early growth stage, like after 3 months of growth, we didn't see much difference. All of them was statistically similar. Same with bacterial communities. We did see some difference. Sweet corn showed higher bacterial communities, and also sweet corn in the pre-plant stage, um, gram negative or gram negative bacteria was similar in all of them, but gram positive bacteria, that was higher in sweet corn and in all rotation crops compared to our bare fallow. Similarly, fungal communities, we have seen that the cowpea and soybean rotation, that actually helped in reducing the fungal communities compared to the bare fallow. And that's what we were thinking, that maybe the reason that if you go grow sugarcane after sugarcane, or sugarcane with rotation with sweet corn, and that may promote some of the harmful fungi in the soil, and that caused the yield losses in sugarcane crop. So over here, as I said, we had the main plots were the bare fallow, cowpea, soybean, and sweet corn, and then we had subplots with different soil fungicides that we applied. So our results showed that crop rotation had significant effect on all of the parameters, yield parameters we collected. Similarly, fungicide also affected most of these parameters. So in our plant cane crop, um, cowpea and soybean was showing higher yields compared to sweet corn rotation, and among fungicides, we saw that some positive effects of mancozeb and mefenoxam. So based on this, we concluded that cowpea and soybean rotated plots can significantly reduce CN ratios. And why that is important, because higher CN ratios can reduce the nutrient availability to the sugarcane crop. And that's important because in our muck soils or organic soils, we don't apply any nitrogen. We are dependent on nitrogen mineralization from the soil, from the organic matter, because these soils have more than 70 to 75% organic matter. And if there's that nitrogen supply goes down because of higher CN ratio, that can affect the following crop. Higher fungi bacteria ratio in sweet corn and bare fallow compared to the cowpea and soybean rotation crops. And over the 2 year cycle, compared to sweet corn, sucrose yields were increased in cowpea and soybean. And even in bare fallow, there was relatively high yield compared to sweet corn rotation. Compared to untreated, fungicide treatments also improved the yields. So that's all I have for now. And thank you very much for your attention. I'm open to any questions.
Great, thanks. We've got a few questions that have come in. So I'll just start with those. And so other folks, please put your questions in the chat. So first question, could we harvest the escaped and now invasive Pennisetum purpurum for bioenergy? So it's Pennisetum.
I think they're talking about the elephant grass, probably. That's what it is. So, I mean, that's not currently in use in crop rotation or in the bioenergy systems over here. What I'm talking about in this is mainly energy cane and switchgrass, and these are the ones which are not invasive. And energy cane is same like sugar cane, but I don't think you can harvest the escaped ones because they are everywhere. I mean, you can just take them out, but it's painful
Right.
to do that.
Yep. And of course, you don't want to grow. So,
Yeah.
All right, next question. Does the energy cane grown in mixed crop systems receive any nitrogen, or is it just relying on excess from the previous crop?
So yeah, that's what we need to figure out in our systems. But you will need to apply some nitrogen based on the literature I found. Like even in our treatments, we are applying some nitrogen in sandy soils where the nitrogen organic matter is quite low, but it should be lower than the commodity crops so that they can get more nitrogen, the excess nitrogen too, from which is escaped from the commodity crops. In our muck soils, I mean, we don't need to apply any nitrogen, so this statement doesn't fit in here because they can, like all the available nitrogen through mineralization in the muck soil should be enough for energy cane. But in sandy soils, you need, depends on like how much organic matter is there, you need to apply some nitrogen, but it will be at the reduced level.
Got it. What are the economic implications of, and this was a question I had, the question is, what are the economic implications of converting 10% to prairie?
Yeah, that's one of the challenges to grow energy cane crops in mixed cropping system or intensified cropping systems. If you do not have um, the market for bioenergy crop, but if you have, then it says that it's not significant in the studies that I showed, because they take that excess biomass and sold that for bioenergy production. And I mean, it may not have, I mean, from the studies, what I found, it's not significant. We didn't do any research on this yet. We are going to start it this year. So then I will know more about in our cropping systems.
Okay. Next question. Have there been efforts to use native plants to achieve the same results?
Have there been efforts to use native plants? It depends. I mean, if the main reason I'm showing that the using of bioenergy crops as in mixed cropping system is because of the characteristics they have. For example, deep rooting system and biomass production. So because of high biomass production, they can uptake higher amount of nutrients from the soil. They because of deep rooting system, they have higher water use efficiency, higher nutrient use efficiency. So even if I didn't come across any studies that used the native plants, but if there are some native plants which have some similar characteristics, that can definitely be used.
Gotcha. Um, I have a couple questions. So how common is it for growers to use any kind of cover crop and where you're at in sugarcane production, or whether it be a mixed cropping system or something instead of a fallow situation? How common is that in actual production now?
Crop rotation is common. We have roughly 50% area under crop rotation, 50% just sugarcane monoculture, where you grow sugarcane after sugarcane. And crop rotation or cover cropping is more common because we have sugarcane on muck soil or organic soils as well as on sandy soil, mineral soil. Almost 70% is on muck soil, 30% on sandy soil. So in sandy soil, because of low fertility, that's almost the whole area is under cover cropping or crop rotation. Because if you grow sugarcane after sugarcane on these soils, you need to put more nitrogen and more fertilizer, and it's not very economical. On muck soil, it's opposite because we don't need nitrogen. And the only need mainly need just the micronutrients. And on muck soil, still, I mean, previously it was even higher area under continuous sugarcane production, like monoculture. But as I said, there is some yield decline or yield penalty if you use that. They save 1 year, but then they have lower yields. But that's why, I mean, crop rotation with rice and sweet corn is kind of common over here.
But not yet some of the other crops you talked about,
No,
cowpea.
that's not there yet. I mean,
Yeah.
that's still under experimental phase.
Okay. Very good. Yeah, that was one of the things that when we did this BMP summit last year, we had some cover crop speakers, and the sort of the feeling that I got was growers were hesitant to use many of the cover crops because they didn't know where to start. There's so many, okay, you have to pick which crop, you have to pick how you're going to grow that crop, and that might change depending on what the preceding crop is, and so on and so forth. So, where do people go for more information on this?
We have for sandy soils, we have some publications, and I think we have EDIS publication too on that.
Okay.
Or I can send the main publication of the cover crops in sugarcane. There is actually more research done on cover crops in sugarcane in Louisiana sugarcane industry than over here, because over here it's in muck soils. The major challenge is to incorporate the biomass into the soil, and that's the main challenge with the sugarcane harvest system too. I mean, we get a lot of biomass from if we harvest it green, but currently it's almost 100% burnt cane harvest because of the challenges with incorporation of the harvest residue into the soil and then plant next crop. So I mean, it's getting more common in sandy soil. Even green cane harvest is picking up, especially in sandy soil. But for muck soil, it's now growers starting to look into it because most of these soils are getting shallower because of organic matter decomposition, and we are losing a lot of soil if we don't grow any crop during the fallow period, or otherwise they keep it flooded. So right now, it's in the interest is increasing as the soils are getting more shallower.
All right. If you don't mind, if you could put that link to that EDIS document up in the chat,
Sure. I mean, if
folks could get it. I just did a quick search. I couldn't find it.
yeah, I will look into it. I know there is a publication, journal publication, but not sure if there is an EDIS document because that was
Oh, okay. Yeah, that would be fine too. If you could get a link to that.
yeah, I can do that.
Yeah, awesome. Let me see. Did I have, oh, one more question. I think we have a couple minutes. So that was cover crops, but this mixed cropping idea is intriguing to me. Is that going on with sugarcane?
It's not going on yet. I mean, it's the our new project from DOE.
Okay.
And that's what we are going to look starting from this year for next 5 years. We are going to look for the mixed cropping in our sugarcane and corn production system. We are going to include energy cane as a buffer crop or in the marginal areas, and to mainly to evaluate its ecosystem services. That includes its effect on water quality, soil quality, and even on the overall production of the commodity crops.
Great. Well, we'll look forward to seeing the results out of that work.
Sure. Yeah,
Thank,
hopefully.
thank you very much for your talk today. And with that, we will transition to Dr. Sharma.
Thanks, Michael.
All right. Thank you.
All right.
All right. Looks good.
From my end, it looks perfect.
Looks good here.
Okay, so time to go?
Yep.
All right, so hi, everybody. Welcome to the second half of today's presentation session. My title today is nitrogen modeling, that using a typical models, something like a DSAT, and then also compare some sensor work that how both can complement in nitrogen management. My name is Lakesh Sharma. I'm assistant professor, soil fertility and sustainable nutrient management specialist and a state BMP coordinator. All right, okay. So although there's a huge push to reduce the nitrogen usage in the agriculture system. If you can see, this is the world NPK usage across agriculture production system. So if you see from 1961 here, oops, let me see. Yeah, so 1961 here to 2014, the nitrogen is basically increasing, and the nitrogen usage is increasing, and it is important to understand why this is a case. Oops, clear all drawing. Okay, all right. So why this is important? Because if we do not use nitrogen, the scenario will look like this. All right, here we have a different color. Let me use this. So this would be the scenario, and this amount of population would not receive any food if we do not apply synthetic fertilizer. And that is important to understand that the nitrogen is required to improve not just yield, but to feed the population. So it is essential to use the synthetic fertilizer, nitrogen fertilizer, to meet the demand of the population for food, and also be a profitable business. So the role of nitrogen, besides all the photosynthetic activity, which we all understand, and you probably have heard about that many times, the focus area is yield and quality. I specifically mentioned here quality, as in many crops, nitrogen drives the quality of the produce, and with yield. Yeah, so if it's a trade-off, especially in agronomy crops, the quality is not a huge factor. Something like a corn, but if you look at the wheat, there is a quality parameter of protein, which we don't grow, but it is a parameter, a quality parameter that nitrogen drives, and other crops and vegetable crops like potatoes. The specific gravity is basically driven by the nitrogen application. So it is important to not just consider nitrogen for yield, but also for quality parameters. So if we apply more than what is required by the crop, this probably the situation. You will have seen some of these pictures in many presentations across Florida and around the world, nationwide. This is a very common process happens after the nitrogen and phosphorus leaves the farms and get into the local water body called eutrophication, and it basically take up all the oxygen and make water oxygen deficient, and that will lead up to the dead fishes. So these are some of the pictures that I got, not just from Florida, across the nation, and all that work started from Lake Erie, and then people start looking for where is the root cause for non-point sources. So 41%, if you see, the picture is not pretty clear, but if you see, I can make, this is a 41% of that farm fertilizer that is responsible for this whole pie chart, the biggest contributor to this situation. So if we cannot live without nitrogen, and we have to apply nitrogen because we have to meet the food demand, and if the same nitrogen is also creating a problem for us, then how to better manage both at that sweet spot, if possible. So this is Florida situation. We have a lot of eutrophication happening and nutrient loading into the water bodies from different agriculture commodities. Okay, so these are the B map that I got this map from Office of Ag Water Policy website, and if you see, there's B maps are everywhere, and that's because the water, the nutrient loading into the water is higher than the standard required protocols, and that's why there's a need to reduce that total load into the water bodies, and to reach to that point, there are BMPs that are implemented, and now by the law will be required to observe and verified across the state. So to meet that demand of reducing these nutrient loads into the water bodies, the BMPs play a huge role, and especially in the nitrogen management. So the current recommendation that we have are mostly depend on the yield expectations, and that's across the several years of research and modified by the soil nitrate test before planting, which in sandy soils in Florida, the nitrate credit or any nitrogen presence is negligible. But there's a need to improvise these recommendations depending on and update these recommendations time to time, and also include the regional climate practices, that cultural practices, temporal variability and spatial variability. So all these factors play an important role, and if we consider these factors, we can come up with a better plan of managing nitrogen. So to do that, typically these are the curves we develop as scientists, researchers when we do rate studies. So this is a typical yield curve. On the x-axis, let me annotate, this is the x-axis, this is the y-axis. So on the x-axis, nutrient application happens. On the y-axis, you plot your yield. So your yield is dependent on your nutrient or a nitrogen that you apply. So as as you apply your nitrogen, there is a spots that after that the nitrogen increase does not it doesn't increase your yield. In fact, it starts decreasing your yield. And to cover that, excuse me, let me. All right. So this is very typical a sweet spot where most of the researcher recommend their nutrient application. So nitrogen application is in this parenthesis where it exists as of now, but most of the farmers' choice is number C, and the reason to adopt the number C is to compensate any loss of nitrogen happened due to environmental factors such as rain in sandy soils, leaching in sandy soils, and volatilization in clay soils. We don't have clay in Central and South Florida, but we do have some clay in North Florida Panhandle area. So that factor play a role to compensate that loss. Farmer apply a little bit more because that's the one, nitrogen is the one driving factor for the yield. So what researchers in UF did, they added some supplemental nitrogen in several across commodities to compensate for any loss due to rain events. So there is a range of between 10 to 20% of additional application of nitrogen if you have a rain event happen that has more than 3 inches of rain over a certain period of time. But some of those parameters does not fall in place when you have 10 inches of rain or more than that, and also the agriculture practices that different farmers follow on their farm. So there is no one recipe for a nitrogen management. Most of the growers have their own nutrient program where they apply their nitrogen. So the ideal rate, why I call this, could be because of the yield side. If you look at the price of nitrogen versus the yield increase, also the environmental factor play a huge role, but it's been studied on various places that before you reach to your maximum yield, your economic benefit start reducing. So your economic benefit is before your maximum yield. So I'll explain that in later my slides, how that play a huge role in both saving the environment at the same time having more money in the farmer's pocket. It sounds odd to many growers when you talk, but when you go over their management program and help them understand the economical part of their nutrient management, it is important that they understand where the yield is can give them the maximum profit versus the maximum yield. So I worked before coming to UF. I worked on potato production system in the University of Maine Cooperative Extension, and we did 3 years of research on nitrogen management in potatoes. The typical nitrogen rate application for the growers is 210 pounds per acre, irrespective of whether they are processing, which is fries there, or a fresh market. And that's very typical. But what we found that 170 pounds per acre is the best rate to reach that point. We have a math to defend this number, and this is on-farm studies, not a single study from the research station was taken into account because it was helpful there, and there were resources to do that. This is a dry land production system, not an irrigated. An irrigated system, something like on-farm research trial, is very difficult and complicated to execute. So I was lucky enough to have a dry land system there, and I did on-farm research. So we divided the whole Aroostook County, which is the biggest county after Mississippi, and then the only county that has more than 90% of potato production of Maine, around 50,000 acres. So we divided the county into Central Aroostook and North Aroostook. There was division was happened on the basis of the data that we collected from these research trials. We saw there's a difference in organic matter. So the organic matter difference was between 2 and 4% and above 4%. And not many sites were above 4%, but we have 4 sites out of 18 research locations across 3 years that behaved very differently, and we separated them out. So we also looked at the factors, something like a cover crop, yes or no, and the potato price and nitrogen cost. So we developed this calculator thanks to Dr. Dukes for funding a graduate student from UF to develop this calculator. So when we developed this, this is just an example of 174 pounds of nitrogen, but when we use this calculator, we found an average of 170 pounds of nitrogen per acre is the best rate to produce the maximum profit and yield and quality of potatoes, because there is a bonus on the quality parameters of potatoes, especially if the specific gravity is between 1.07 to 1.09. And if your specific gravity is 1.08, most of the farmers get a bonus from contractors, which is McCain food there. All right. Okay. So we have that covered here. Okay. So if we think about corn, this is the picture that I got it from Dr. Jim Shepard from Nebraska. He is the pioneer for sensor work with Dr. Bill Ron. So if you see that typical Midwest corn planting, which happens around April, May, and then 80% of the nitrogen taken up by after V8 leaf stage, and the V8 leaf stage is basically 8 leaves on that plant. So most of the Midwest farmers, they apply their nitrogen before planting or at planting, and it's never taken up for a month and a half. In our case, we do lots of split applications, but we need to investigate what timing is the best for that big nitrogen application. We do splits across the corn growth cycle. Most of the growers are doing between 7 to 10 nitrogen splits. So, but the biggest chunk is required when after some around wheat and leaf stage, when corn take up most of the nitrogen that's supplied. So this is important to understand, and how that could be done. There are some tools, something like modeling tools and some sensor tools that we can use to mimic the crop requirement along with the irrigation. So I would give a full credit to Dr. Dukes and Dr. Wendy Graham and their team for modeling for 5 years study of irrigation and nutrient management in live oak area. And they used a DSAT and soil moisture sensor work. And if you see that in both cases, they able to reduce the nitrate leaching by 24% here by using a DSAT model, and 37% using soil moisture, soil water sensors in corn. So these are some of the modeling techniques that being used in Florida and have shown promising results to reduce nitrate leaching. And the typical nitrogen rate that was used for optimum yield at the same time reducing nitrate leaching was 247 kg per nitrogen per hectare, which if you convert into pounds per acre would be somewhere around between 240 ballpark. So so there is a definite need for revisiting nitrogen rates from 210 onwards, but there is definitely no sense to apply nitrogen beyond 240 pounds. We have an ongoing project on that, and we will come up with a recommendation after a few years. There's a few other studies being done on many other places. I'm covering as much as I can, depending on the cultural practices we have in Florida. So if you see that, for some reason, here is a no-till and compost application that reduced the nitrogen leaching. So that was also modeled, and we have no-till and strip-till practices in corn production system, and there are some compost application in citrus and some other crops, and there is instances where the research has shown a significant reduction in nitrate leaching when these two are used in combination or individually. So there are some ways that farmers can reduce their nitrate leaching and improve their yield or maintain the yield they have. Okay, so here is a nitrate leaching modeling here again for I think this is the study that was done in Canada, and there was a 50% reduction in nitrate leaching using neutral network, and this is 180 kg nitrogen per hectare. If you look at the Midwest recommendation, their recommendation is more as you go north. I would call it as you go north, Midwest and Canada, their recommendation are more close to the 200 pounds per acre ballpark. So and there is several long-term multi-state studies being done from last 15 years in Midwest and North of that that determine that if the farmers apply more than 200 pounds, there is no credit to the yield. So a general consensus is that on sandy soils, you may need to apply nitrogen across the production system, across the crop growth cycle to meet the need of the sandy soil, because it doesn't hold nitrogen well enough. But at the same time, to compensate some of the losses from the rain, there is some supplemental nitrogen. So if we call it the study Dr. Dukes and Dr. Wendy Graham has done on for 5 years, it makes perfect sense to the nitrogen number is 240 pounds per acre, because it compensates that loss of nitrogen across on some years of high rainfall. Okay, so these are some of the models that I thought are important to consider, where we are also focusing on these modeling techniques for our study that's going on in corn presently. We are also using some sensor technology to learn if there is a possibility to manage nitrogen more efficiently. So so I'm using sensors, and I've used these sensors. These are sensors use a red wavelength and red edge wavelength. These are the wavelengths are in the range of 700 to 1300 nanometer. Those are called red edge or near infrared. And between 500 and 700, I'm talking about this 500 here and 700 range, are called red wavelength. It is important to learn that the after 700 nanometer, the wavelength is called red edge, because if your sensor doesn't have a red edge and you're using on a crop that is a very high biomass, something like corn or potatoes, your red wavelength will be saturated. And that way you won't be able to develop an algorithm to calculate your nitrogen, which means, predict a nitrogen or estimate your nitrogen requirement. So this is a reading that comes out of these sensors called NDVI. You have heard about this acronym many times. This is called Normalized Difference Vegetative Index. This is one of the vegetative index that you can calculate using these wavelengths, but there are several other indices that you can use. The NDVI is the most promising and being widely used among all those indices. So that's my preferred indices as well. So these are the sensors that emit light. So let me go back and pick a color, because I think the color. All right, so this is a source of light. It's a LED source. It is basically any LED source that you are also using at your house. Basically, your remote TV remote is a LED sensor. It talks to the TV because they have the same frequency and the wavelength they talk to. So we are your car remote is basically the same technology. So agriculture scientists developed this technology to learn if there is a possibility to estimate nitrogen requirement by the crop. So the light is emitted from this source to the target. Our target here is our crop, and then after it emits all light is absorbed by the target, which is your crop. It reflects some of the light, because not all the light is absorbed by your crop. Similarly, sunlight, part of your sunlight is absorbed by the plants and partly reflected from the plant. So the LED source from this sensor emit a light on the crop, and some part is absorbed and some part is reflected, and the sensor has 3 or more filters that absorb the reflected light. And the reflection of the light depends on how healthy your crop is. So suppose your crop is not healthy, that means there will be more reflection, because crop is not absorbing enough light, because less photosynthesis, less nitrogen, more nitrogen deficient crop. So if your crop is healthy, there will be less reflection. So depending on this principle of reflection, the sensor delivers us a reading called NDVI that we talked about. So this is how you can use on a commercial basis. If you see these sensors on the applicator, fertilizer applicator boom, and it's a real time. So there is an algorithm that's basically a method of calculation, estimating the nitrogen requirement, and that method or a math incorporated in the controller that's in the tractor cab. So basically this is a GPS mounted tractor where driver is just driving the tractor, and the controller is talking to these sensors and calculating the nitrogen in real time. And it sounds like a lot of things are happening in real time, but all this happens at the speed of light. So so the speed of light and typical speed is 5 to 10 miles an acre, 5 to 10 miles, and on that speed, this nitrogen estimation happens pretty efficiently. So I use these algorithms for potatoes, and there are two different methodologies for these sensors. One methodology is from University of Nebraska Lincoln, and one methodology is from Oklahoma State University. Both works pretty well. I personally prefer Oklahoma State University because that's more easier for the my clients to understand and the growers to follow. So depending on that, you can pick whichever you want. So I picked Oklahoma State, and then I calculated the INSEE, which is in-season estimation of yield. It is not a nitrogen calculator. It is estimating a yield. Depending on the yield estimation, it calculates it estimates the nitrogen requirement. So just to be clear on that. So in-season estimation of yield is calculated by sensor reading, which is NDVI, divided by the growing degree days from the planting date. So, and again, it all happens in the real time. So sensor readings divided by the growing degree days from the date of planting to the date of sensing, it gives you in-season estimation of yield. And all is done by the algorithm, the math already calculated. So there is no need for any producer to do that. So these are the relationships that I developed in potatoes in Maine. I'm working in Florida for similar work. If you see here, this is the tuber yield on x-axis. This is the chlorophyll index on the x-axis, and tuber yield on the y-axis. So when you develop this relationship, the R square is 69%, almost 70%, which is very strong. So on a field study, it's a very good relationship. It's a correlation. So that means your algorithm is very efficient in predicting your yield. So depending on the R square value, it determines. And also it was significant on 0.05%. So we were very confident that this algorithm is very robust. Okay, so then we used these sensors in a real time. So here is a yield from farmer practice, which is some part of the total nitrogen program. If the total nitrogen requirement from the farmer is 200 pounds, he applied 50 to 80 pounds at planting. I'm talking about Maine here, not Florida. You won't apply that much nitrogen at planting. So farmer applied around 50 to 80 pounds at planting, and he also maintained a very high nitrogen application field. And that strip, it could be called as nitrogen rich plot. And the nitrogen rich plot could be as wide as your applicator, the farmer applicator, and it could be as long as 100 feet long. So the sensor estimated the yield from high end plot, and it also estimated the yield from farmer plot. And this is the yield difference. So this is the yield difference that comes from high end plot and farmer plot. And then this difference will be calculated by using an algorithm. And depending on this yield difference, the algorithm will estimate the nitrogen requirement. So let's go ahead and calculate how much nitrogen we need. All right. So for an example here, 280 pounds of nitrogen per acre was applied on high nitrogen plot, and our sensor estimated a yield of 315 hundredweight. And farmer applied 120 pounds of nitrogen per acre on its plot, and the sensor estimated 290 hundredweight of potatoes. The difference is 25 pounds. When you multiply that to convert into the pounds, total pounds, the total pound difference is 2,800 pounds. So 2,800 pounds, 2,800 pounds multiplied by the nitrogen uptake, which is 0.018. It's basically 0.18%, is 50 pounds of N. So 50 pounds more N is required to compensate that. But our efficiency is not that high, which we already compensate that. So the efficiency is 63%. It's very promising under dry land system. On irrigated, it could be more, but I'm talking about the control situations here. On a real world, this efficiency could be in the range of 45 to 55. So when we consider that efficiency factor, the total nitrogen required was 79 pounds to meet 350 hundredweight of potatoes. And if we go back, if we go ahead, the farmer rate was 225 pounds. That was what the farmers was planning to do. Our rate was 120 plus 79, almost 199 pounds per acre. So if you consider the difference is 26 pounds of nitrogen multiplied by the pound per acre rate price of nitrogen, which is it's 92 cents. That was calculated using price of nitrogen plus labor plus tractor application, transportation, all those costs usually added up to 92 cents per pound cost. And when you multiply that, if somebody has an 800 acre of potatoes, the person is saving around roughly $19,000 per year. That's a lot of money that person can save. So the end saving total was 26 pounds per acre multiplied by 800 acres was 20,000 pounds per farmer. So it tells a story that there is a possibility to reduce the nitrogen. There is a possibility to use the technology to manage this nitrogen efficiently on several crops. I worked in corn, that is agronomy crop. I worked in potatoes, which is a vegetable crop, horticulture crop. And in both situations, there was a huge credit for them, not only on the dollar side, but on the nitrogen side as well. So, so that means technology works, but what it needs, what is a summary of all that is technology has improved nitrogen prediction, and we saw that. Then that is a very robust research over a 3-year period in potatoes from multiple on-farm trials. So robust data across multiple years is required to develop sensor algorithms and modeling. What I just think here is that similar work need to be done in Florida to reach to that point. Multiple models must be compared to determine the best suitable for Florida conditions, just something like Dr. Dukes and Dr. Wendy Graham team has done. They compared 2-3 models that are suitable or that are more promising to use in Florida conditions. Growers need a different thought process to improve the agriculture practices and nutrient loss. So my old professor one time said that if farmers that are we call them progressive farmers versus an average farmer, they have very different mindset to improvise their agriculture practices. So that means if you're a farmer and you want to adopt these practices, there is definitely an edge to improve your nitrogen management. And society needs to understand that crops cannot be grown without fertilizer, which I have shown in first of my slide, where if we do not use synthetic fertilizer, half of the population that we have on the earth would be left unfed. So there is no way we can meet the demand of that population without using fertilizer. But at the same time, the people who use fertilizer need a special, very different mindset to improvise their practices. With that, I would say I am open to any questions if anybody has any.
All right, put your questions in the chat. We don't have any yet, but I was wondering, so you developed that tool, the fertilizer tool for Maine. So are growers now using that before they weren't?
That's a good question. So,
I mean, I know you left Maine, right? Kind of as you were finishing that up. So,
no, that's a good question. So there's a team from that I work with that uses a drone technology, not a sensor technology. So we give this algorithm to that team, and that team actually started working with us from the day one, and they are industry partners for using sensor technology, from using a drone to calculate or estimate these nitrogen rates. So they are working with the 5 different selected farmers that are from McCain Foods, that work with the McCain Foods. So there's a McCain Food agronomist and 5 selective farmers that work with this this industry partner in a real time. So this guy goes on their farm, fly the drone, come back, and the next day he tells how much nitrogen is required on their farm. And he also sent that prescription maps that talks to their GPS systems. So the prescription maps are actually uploaded in the controller and done. So the farmer goes and they are not doing on all of their acres. They are also doing on 50-acre parcel on each of these farmers. So it's like an initial phase where the farmers are basically working with the industry partner to get confident to use this technology on their farm. So all 5 farmers have between 50 to 70 acres of parcel where this guy is working with to implement this technology.
okay.
But all happening as all together. So there's an industry partner, there's a contractor, and then there is a farmer.
Yep. Mike Mulvaney asks, for sensor-based end application algorithms, how wide of a geographical area do those algorithms apply? So how site-specific are they, or are they generalizable?
Good question, Michael. They are based. So that's one drawback of these technology, that if you want to use that technology in a specific state where the cultural practices, weather, climate, soil is different, you need to develop a algorithm for that specific region. And even within the state, we found that in Maine, the northern Maine had a different algorithm versus central and southern Maine. So so there is a need to develop a separate algorithms for different states, and within the state, different regions, depending on what kind of climate you have. So if I see something like corn or cotton is grown, just assume that it's grown in Central Florida and in North Florida, I would not see a one algorithm. I see 2 different algorithms for 2 different areas.
Next comment that says that this was a lot to unpack, and this viewer says there's a lot of tools out there that need to be adapted for Florida. And in my mind, this is the analog to this is variable rate irrigation. we know that there are regions of the country where that has become popular. South Georgia, for example, with center pivots, but we also know that a small fraction of growers utilize that technology to its optimum. So I'm kind of drawing a parallel here, thinking this could be a similar situation until it's mainstream, particularly if the algorithms are regional or even sub-regional. That's a real challenge, but that's why you're here, right?
Yeah, that's why.
All right. Our friend Vivek asks, can we use NDVI versus N application relationships in the crop initial growth stages when the sensor can sense both crop and soil surface?
All right, so this is a very important question. I work with mostly with the crop side. I have not used and I haven't seen. That could be a question, maybe if somebody from AI team could answer this on how the sensor behaves when they see soil versus crop. I can tell you that the readings will be very low, but is there a way that the sensor can estimate the nitrogen requirement when the crop is not up? You just plant it, and crop takes 20 days, 15 to 20 days to germinate, depending on the temperature, soil temperature. But if there is a possibility to determine before at planting or between that window, that is definitely a good question, and I may not have an answer for it at this time. As I said, maybe somebody, if from AI team could answer if they are.
Well, the short story is, I think next week we have Dr. Yanis is going to be talking about AI and sensing. So save that question for then, Vivek. But Vivek asked a follow-up question. Can we use soil adjusted vegetation index instead of NDVI?
Yes, we can. There are VI indexes, vegetative indexes, that have actually calibrated already from Nebraska, maybe your alma mater, and you can use any one of them to see which one is more fit to your conditions, because I have worked with all of them, and I found NDVI is the best, works for corn and potatoes. But there are certain regions, especially in Asia, they use VAI, and there's a LAI. So they use LAI, leaf area index, and VAI, vegetative some index. I forgot the name of that VAI, and they are more useful for them. And so it's again, you need to calibrate that specific vegetative index for your needs, and this could be replaced with SAVI. Yes.
Okay, well, I think that was our last question, and we are about out of time as the rain starts here in Gainesville.
Yes, that's true.
Thank you, Lakesh. Thank you, Hardev. And thank you, everybody who attended today.
Thank you, everyone.
Thank you, Michael. Thank you, everybody.
Thank you, Mike.
Have a good rest of the day.
You too. Thanks.
You too.
All right. Bye-bye.
Bye.